after 5 seconds. Alright, let's try another problem. A wheel mounted on an axle that is not frictionless is initially at rest, omega 0 equal to 0. A constant external torque of 50 Newton is applied to the wheel for 20 seconds, giving it an angular velocity of 600 rpm. The external torque is then removed and the wheel comes to rest in 120 seconds. A. Find the moment of inertia of the wheel, and B. the frictional torque that brings the wheel to a stop. Now you apply external torque and the wheel rotates. When the external torque is removed, the wheel comes to a stop. Why? Because of the torque applied by the friction, and we need to find that torque. Alright, well, disregard this. I just put in a wheel there that is rotating. Now what are the data we have? Omega 0 equal to 0. Omega F is given to be 600 revolutions per minute. Convert that to radian per second. Multiply by 2 pi and divide by 60. So omega F is 20 pi radian per second. Tau equal to 50 meter Newton. Well, the external torque applied is 50 meter Newton and the time is 20 seconds. So when an external torque of 50 Newton applied for 20 seconds gives it this angular velocity. Well, we first find the angular acceleration. Tell me, what will be the equation we will use to find the angular velocity? Well, we can find the angular velocity by knowing the initial angular velocity. We need to find the angular acceleration. We know the initial angular velocity, the final angular velocity, and the time, and that's enough for us to find the angular acceleration. So omega F equal to omega 0 plus alpha t, or alpha equal to omega F minus omega 0 divided by t. That will be omega F minus omega 0 is 20 pi radian per second divided by 20 seconds. That is pi radian per second squared. That is the angular acceleration. What are we looking for in part A? Find the moment of inertia of the wheel. Can you tell me how we can obtain the moment of inertia if you know the angular acceleration and we know the torque that produces that angular acceleration? What is the relation between the torque and the angular acceleration? Tau equal to I alpha. Well, tau equal to I alpha, we can now find I, the moment of inertia. So I equal to tau divided by alpha, that is 50 meter Newton divided by pi radian per second squared, and that is 50 divided by pi kilogram meter per second squared. We can leave it like this as an exact answer. So we now have the moment of inertia of the wheel. In the next part, the external torque is now removed and the wheel is now going to come to a stop under the action of the frictional torque. Alright. Now when the external torque is removed, the frictional torque, let's call it tau F, produces a negative angular acceleration, bringing the wheel to a stop. And we have omega 0 in the beginning, that is the moment when the external torque is removed, the wheel is rotating with this angular velocity. And its angular velocity is going to come to 0. So omega 0 is 20 pi radian per second. Omega f equal to 0, and the wheel come to a stop in 120 seconds. And we also know that the moment of inertia of the wheel is 50 divided by pi kilogram meter per second squared. Alright, what do we do first? We have enough information here to find that acceleration produced by the frictional torque. So let's do that. We first find the acceleration caused by that net torque applied by the friction. And how do we do that? Omega f equal to omega 0 plus alpha t. We know omega f, we know omega 0, we know t, therefore we solve for alpha, and using the values omega f equal to 0, omega 0 is 20 pi radian per second divided by 120 seconds. That is negative pi over 6 radian per second squared. So the frictional torque produces a negative acceleration of negative pi by 6 radian per second squared. Well, we know the acceleration caused by the frictional torque. We know the moment of inertia of the wheel. Can you use these two quantities to figure out the frictional torque? Tau f equal to I alpha. I is 50 divided by pi kilogram meter squared times alpha is negative pi over 6 radian per second squared. And you see the advantage of leaving the answer in the exact form. You can see the pi and pi will now cancel. That is negative 25 over 3 meter Newton is the frictional torque. Alright, that's a good problem, and I want you to learn how to do problems like this. Okay, another one. A light meter stick is loaded with masses of 2 kilogram and 4 kilogram at the 30 centimeter and 75 centimeter positions respectively. What is the moment of inertia about an axis through the 0 centimeter end of the meter stick? What is the moment of inertia about an axis through the center of mass of the system? Use the parallel axis theorem to find the moment of inertia about the axis through the 0 centimeter of the stick and compare the result with the results you have in part A. Well, moment of inertia of an object of mass m situated at a distance r from the axis of rotation. Do you remember that equation? What is the moment of inertia of an object of mass m placed at a distance r from the axis of rotation? It is mr squared. The moment of inertia of an object placed at a distance r from the axis of rotation is mr squared. So we can now, in part A, we want to find the moment of inertia about an axis through the 0 centimeter. That means about an axis passing through the 0 centimeter of the meter stick. Alright, the moment of inertia of a mass m situated at a distance r from the axis of rotation is given by I equal to mr squared. So we can now find the moment of inertia of these two masses about an axis that passes through the 0 centimeter mark using this relation. For the axis passing through 0, m1 is at a distance r1 from the axis of rotation, and m2 is at a distance r2 from the axis of rotation, where r1 equal to 30 centimeter and R2 equal to 75 centimeter. Okay, let's look at that again. Now, what is the moment of inertia of object 1 about this axis? We are looking for the moment of inertia of these two objects about an axis that passes through the 0 centimeter mark. So, moment of inertia of M1 about the axis that passes through 0 will be M1 R1 squared. Moment of inertia of M2 about the same axis will be M2 R2 squared. The total moment of inertia will be M1 R1 squared plus M2 R2 squared, and we know those values. M1 is 2 kilogram, R1 is 0.3 meter, M2 is 4 kilogram, R2 is 0.75 meter, and that gives us 2.43 kilogram meter squared is the moment of inertia of these two objects about an axis passing through the 0 centimeter mark. Okay. First of all, we need to find the moment of inertia of these two objects about an axis that passes through the center of mass. Well, in order to do that, we need to know where the center of mass is. Where is the center of mass? X center of mass is M1 x1 plus M2 x2 divided by M1 plus M2. Now, M1 is 2 kilogram, x1 is 0.3 meter, plus M2 x2 is 4 meter times 0.75 meter divided by M1 plus M2, and that is 0.6 meter. So the center of mass is 0.6 meter. We now need to find the moment of inertia of these two objects about this axis that passes through the center of mass. Well, the moment of inertia of M1 about that axis will be M1 times the square of this distance. Is that right? Okay, let's put that down. The distance of M1 from the center of mass is R1 equal to 0.6 minus 0.3. This distance is R1, and that R1 is, up to here it is 0.6. 0.6 minus 0.3, that is 0.3 meter. The distance of M2 from the center of mass is, what is that distance? The distance of M2 from the center of mass is this distance, R2. And what is that equal to? 0.75, 75 centimeter. 0.75 minus 0.6, that is 0.15 meter. Alright, the total moment of inertia about the axis that passes through the center of mass is M1 R1 squared plus M2 R2 squared. And we know those values, 2 times 0.3 squared plus 4 times 0.5 squared, that is 0.27 kilogram meter squared. That is the moment of inertia of these two objects about an axis passing through their center of mass. Okay, now the third part is